Hey everybody, Mr. Piercy here. What we're going to be discussing in today's lesson is angles, how they're classified, particularly how they are measured and named. So what you see here in the diagram, it kind of gives you a definition of what an angle is. It is two rays that share a common endpoint, and the middle column tells you how we can name it. So make sure you read that. If you're having a little hard time reading it, you could call it, here they're saying angle A, here they're saying angle BAC, here they're calling it angle 1, angle 1. Ah, the right tool here. And of course, that symbol right there is the symbol that we use for recognizing an angle as we, like if we were typing something up or writing something out, that's the symbol that we use for an angle. So what are two other names for angle 1? Well, these are fairly straightforward. Angle number 1 is looking here at those two rays. The two ways that we could name it would be angle JMK or angle KMJ. And for angle 2, let me pick a brighter color here. Angle 2 is adjacent to angle 1. It shares the side MK, so those are adjacent angles. How could we name that one? Same basic concept. Take the 3 points that make up the rays and call it KML. And we can call the other way that we can name it would be angle LMK. So the question at the bottom is one that I would like you to think for a moment and write your own answer down before I put mine up on the board. So would it be okay to name angle 1 angle JKM? Yes or no? But be able to provide a complete sentence as your answer for your explanation. So go ahead and pause the video, answer it, write down your answer, and when you're ready, hit play and see what I write. So here we are, JKM, angle JKM. Is that a good name for angle 1? And here I'm going to say no. Angle JKM isn't a good angle name because the common endpoint or the vertex of the angle must has to be the middle letter when you name an angle. So unfortunately, JKM would not work. So here, what we see in this diagram is we're kind of taking a look at how angles are measured. At the bottom, you see the 4 typical angle classifications that you're used to seeing from prior math classes. An acute angle being something that's greater than 0 but less than 90. A right angle is exactly 90. An obtuse angle is greater than 90 but less than 180. And a straight angle is exactly 180 degrees. Now I want you to kind of pay attention to this bit right here, particularly the equal to part, where it's saying the measurement of angle COD is equal to the absolute value of C minus D. That is pretty much tying back into what we talked about with the ruler postulate with segments. A measurement of an angle in degrees cannot be negative. It's impossible for an angle to have a measurement that is a negative number. Negative angles do exist. Negative angles do exist, but they indicate a direction that something is turning. Just to give you since we're talking about it, just to give you a brief idea of it, I'm going to put it over here on the right side of the board. Your graph, quadrant 1, 2, 3, and 4. Why are they named that way? Positive angles go counterclockwise, and negative angles go clockwise. That's all positive or negative indicators. That's what negative angles really mean. It just indicates a direction that something is turning on the coordinate grid. We're not going to really do that in geometry, but since I'm mentioning negative angles, I figure I'd go ahead and give you a little bit of information there. Negative angles don't exist as far as a measurement. They can only exist as a direction. So it doesn't matter how you're measuring your protractor, your number has to be a positive number, and that's what the box is telling you with the absolute value of the 2 points where you're subtracting them. So at this point, I would like you to kind of pause the video and maybe come up with an example of a real-world example of each type of angle. And what I would like you to do is maybe in the comment section of the video in the Google Classroom, maybe give what you thought was your best one out of the 4. Which is the example that you thought would be the best one? So an example of an obtuse angle, for instance. I'm just looking around my room to see if I can come up with anything off the top of my head. And I'm looking at the hands on my clock. The hands on the clock would represent an obtuse angle because the time I'm making this video, it's right around 5:51, which is making an acute angle with the hands on the clock. So just pause the video, come up with a few examples, and share them in the comment section of the classroom. Moving on, this is how we're going to be measuring angles. The device that you see is a protractor. We will be using it for 2 primary purposes. One is really to just make a straight line. We'll use the straight edge of the protractor when we have to do constructions, not so much to measure how long something is in inches or centimeters, but just to create a straight line. The other thing that we'll be doing with it is measuring angles. Now the picture that you see here is how you actually measure an angle with a protractor. The vertex of the angle goes onto, depending on what type of protractor that you have. It might have a hole like this diagram does. It might give you a perpendicular set of intersecting lines here to show you where you'd place the compass at the vertex of the angle. I'm sorry, the protractor, the vertex of the angle. But then we would line usually one ray up with the base of the protractor, and then wherever the other one kind of comes out, we would follow it out far enough to see, well, where does it touch the number line on the compass. So we have 3 angles that we're going to be measuring. Angle LKN, and that's kind of the one that I'm highlighting on the protractor, angle LKN. So if I am measuring this for real, I'm going to put the compass here at the vertex of the angle, line one side of the protractor, that base line up with one side of the angle that we're looking at. And I'm actually going to follow this line out because when we start counting, we always start counting at 0. And you can tell on the number line that goes around the arc of the protractor, we have 2 number lines. So always start at 0. So I'm going to start at 0 and kind of follow it around until I get to here. And that's where I'm going to start reading it. Now clearly this is an obtuse angle, so it should be greater than 90 degrees. And when I'm looking at it here, it's looking like it's halfway between 140 and 150. So I would say that the measurement of this is 145 degrees. So if you haven't already kind of started speeding up, you could probably very easily see what the measurements of the angles are going to be. I'm going to just go ahead and highlight them here so we can get let's pick a different color here. JKL is right here. Now this is where we're measuring it not using the base of the protractor anymore. So we're kind of looking at the absolute value difference between the numbers. It doesn't really matter which ray you start off. Where if you say you start where point J is or you start where point L is, it doesn't really matter what ray you start with. But I am going to start here where the 90 degree is for point L or for point J, simply because it's at a whole number. And I'm going to just count. Here's 10 degrees, 20, 30, 40, 50. So that one looks like it's going to be 55 degrees. So I'm going to say the measurement of angle JKL, oops, not 550, 55 degrees. And we've got that one taken care of. And the last one we will look at together as a group, real quick, JKN. Well, here's J, here's K, and here's N. And that one's real easy to tell. That one's right at 90 degrees, so the measurement of angle JKN is equal to 90 degrees. So if you're having any questions about how you measure a protractor, again, just like any other lessons that we're doing, make sure you write these questions down and post them to me in the comment section or email them to me directly, and I'll be happy to get back with you as soon as I can. So here's an example where we're really talking about congruent angles. We're just trying to determine which ones are the same. So the diagram on the left, where we have them labeled A, B, C, D, and so on, we're trying to compare it. Are they congruent to the angle that's on the left? Which angles are the same or not? All right, so looking here, the question at the bottom says, is the size of an angle determined by the length of its rays? Now, the angle that I have here on the right, I can kind of take it and match it up here and see, we can see, well, that one, those two really don't look like they're congruent. And maybe if I kind of put this one here and need to do a little bit of fine tuning, are those congruent? Well, they don't look exactly congruent. So let's try and find one here. Let's turn this guy around and see what happens in those. That one looks pretty good. So here it looks like this angle matches, okay? But the question is, the angle matches, but it doesn't look like the rays really do. So the question that we have at the bottom, it says, is the size of an angle determined by the length of its rays? And at this point, again, I want you to think about how you're going to construct a complete sentence. Remember, a complete sentence should have an element of the question inside of it, and any math vocabulary that you use should be obviously used appropriately. So at this time, pause the video and write out a statement to answer this question, yes or no. And when you're done, push play again and compare your answer to mine. So here, is the size of an angle determined by the length of its rays? Here is my response to that. No, the length of the rays do not determine the size of the angle. Rays are indefinitely long, so how long they're drawn doesn't matter. The size of an angle is determined only by its measure in degrees. So here I actually wrote 3 sentences to answer the question. Here, looking at these 3 angles, I'm sorry, these 2 angles I should say, angle C and the one that was off on the right, even though their measurement is the same and their rays are different lengths, that tells me that even though the rays are different lengths, just because of the way that they're drawn, doesn't mean that they're different angles. It is the measurement of the angle itself, and in this case they're the same, so I would say these 2 angles, yes, they are congruent to each other. So moving on, here the last thing that we're really kind of taking a look at is just congruency symbols. How do we determine when angles are or not congruent to each other? In the previous lesson, talking about segments, we used hash marks to determine whether segments were the same length or not, whether they were congruent. Usually, not always, but usually you will see arcs indicating congruent angles. For instance, on the triangle, the set of triangles on the left side that are just in black and white, let's take a look at angle E. Angle E has a single arc in between its 2 rays. So on the triangle on the other side, angle X also has a single arc. Well, those markings are what allow me to determine that they are congruent to each other. Angle F has 3 arc lines on it. So angle Y also has 3 arc lines on it, so that means those must be congruent also. Well, what about angles that have different? Let's take a look at angle E again. And let's take a look at angle W on the other triangle. Because angle E, and I don't have any idea what the measurement actually is, whatever it is, angle E has some number. Angle W has some different number, and I know that they're different because angle E has 1 arc line and angle W has 2. The different arcs in between the angle, or in between the rays that make up the angle, tell you that they must have a different number, and therefore they cannot be congruent. And here on the triangles on the right, these are a little bit harder to see because they're kind of trying to color code it, but they're also marking them slightly differently. If you notice, angle A has 1 arc line, angle B has 1 arc line, and angle C also has 1 arc line. But on the arcs themselves, they're a little hard to see. There's 1 little hash mark, 3 little hash marks, 2 little hash marks. So I'm adding these here just to help us see them a little bit more clearly. And that is another way of distinguishing when when angles are congruent or not. So here I can say the angles on the right, the triangles that we have, I can say angle A has to be congruent to angle D because even though all of the angles in both of the triangles have 1 arc line, the hash marks on the arcs themselves are helping us distinguish when things are congruent or not. I can say angle B would be congruent to angle E. Now, I do want you to understand the triangles that you see here on the right that are using little arcs with the hash marks on them, that is not something that I typically see a lot of, but you might see it from time to time, so I wanted to make sure that you include, that I included some examples. The ones on the left where they use different number of arcs themselves, that is much more common, at least in my experience. Maybe it's different in different regions of the country, I don't know, but I know that for what I've always taught, what you see with the pair of triangles on the left is more common than what you see with triangles on the right. But I wanted to make sure that you saw both kinds. So that's pretty much it as far as how you name an angle, how you measure an angle, and how you determine whether angles are congruent or not. So again, as always, anytime that you have a question, anything that you have thought about that you want some clarification on, make sure you write it down and talk to each other about it. Send me an email, leave me a comment in the sections of a Google Classroom, and I'll be happy to get back with you as soon as I can. But until next time, guys, thanks for watching. See you soon.